Hello and welcome to the Calc 1 Exam 2. This is our first part of review. Well, for this first page, there's not going to really be anything, so we'll go on to the next page, which is also blank, so we'll go on to the page after that. And here we actually get our first problem. So, this is question number 1, a bunch of different parts of it, but part I is going to be, and these parts maybe not be connected, they're just like all touching on the same idea or format. So, it tells us, suppose f prime of x is sine of e to the x. So they give us what our the equation of our derivative. They also tell us that f of 3 is 1.67. And we need to use linearization of f at x equals 3 to approximate the value of f of pi. So, linearization. So how we're going to do this is if we're trying to figure out, and I'm not use the exact formula that they have, I don't have that on me, is that if there's some f of a that we want to approximate, and we don't have like the ability to just like approximate that, right? Well, it's going to be equivalent to, I'll say, some f of x naught, where x naught is like a point that's more convenient to use, plus f prime of x naught times a minus x naught. That'll give us a rough estimate. You can almost think about this. This comes from the equation of like a line, like y minus y1. If you add the y1 over to the other side, you have y equals y1 plus m x minus x1. That's kind of where that's coming from, and it's a good way to approximate. So, in this case, we don't have a value, like we don't know what f is. We know f prime, but we don't know f. But we want to try to get a value of pi, and pi is a weird number to even like deal with because it's like all infinite and stuff. So we're trying to figure out what f of pi is, and we're just going to try and approximate it. Well, it's going to be f of 3, which we're given, plus f prime of 3, which we know what f prime is, so we can figure that part out, times, it's going to be pi minus 3. So whatever like the difference is like between what we want to approximate and like a nice place that we do know information about, that we're going to multiply our derivative times that difference. So f of 3 we know is 1.67, and f prime of 3 is sine of e to the 3, and I'm just pi minus 3. I'm going to go ahead and plug it into my calculator, and what I got is that f of pi is approximately 1.804. In good news, that's answer choice A. Going on to II, the second one. The graph of the derivative of g, so this is not the graph of g, this is the derivative of g. They bolded it because it's really important to know that. Identify which of the statements are true. So, let's start looking at this. So our first thing is x2 and x4 are critical points of g. And look, just glancing at it, it might be tempting to say, oh look, the derivative here is 0, we're fine. But here's the thing, this graph is the derivative. So the derivative here is actually some big number. The derivative here is some big number. We don't know what the number is, but it's not 0. Because this y is g prime. So our derivative isn't 0 there. So that means that they are not going to be critical points. So I can rule that one out. In positive elimination, that means that A is going to be wrong and B is going to be wrong. Okay. G of x3, so we're looking at this one, is a local extreme value of G. Well, while right here, this is on the x-axis, so that means that G prime of x3 is 0. So that's part of being extreme value. That is a critical point. We know that, but here's the issue. Local extreme value means it has to be a maximum or minimum. We don't just want our derivative to be 0. We want it to be changing signs, right? So if I were to try to draw this, to our left, our derivative is positive because it's above our x-axis, and to the right, our derivative is positive because it's above the x-axis. So it means that we have a positive slope, and then we have a 0 slope, and then we have a positive slope again. That's not a minimum, that's not a maximum. So that's not going to be true. That also means that D has to be wrong. So x1, x3, and x5 are critical points of G. Well, critical points are where your derivative is 0. This is the derivative graph, so we look for the intercepts, or x-intercepts of our derivative graph. In that case, we have an x-intercept here, here, and here. And what are they? x1, x3, x5. That one is true. I agree with this one. I'll just put a little check mark on the side. Okay, let's go on to the next one. x2, g of x2. So basically, at this x coordinate, at this x coordinate, and this x4 is the next one. In this x coordinate, so x2, x3, x4, and their corresponding y values are inflection points of G. So inflection points are where our second derivative is 0. In other words, where the slope of G prime is 0. So if I'm looking at the derivative of G prime, well, I have a positive slope everywhere, but at x2, that has a 0 slope. So that means that because our graph is G prime, that means that G double prime, which is the derivative of G prime, is 0 there. It's 0 there. It's 0 there. So we kind of look for this the same way that we can figure out our critical points on the graph of the original function. Well, given the graph of the derivative function, what looks like your critical points, you can't see, I'm putting those in like air quotes, are going to be your inflection points here. So like everything is like shifted. So this one is going to be true. So the question, which from there we could figure out that it's going to be E because that's the only one that has 3 and 4 being true. But just to work through it, let's look at 5. G of x1 is a local minimum of G. So to be a local minimum, you need to be a critical point. So your derivative has to be 0. Well, at x1, it's on the x-axis, and this is the derivative graph again. Cannot emphasize it enough. So our derivative is 0 there. The other thing to be a local minimum looks something like this. To our left, we need to be decreasing. To our right, we need to be increasing. So to our left, this section, we're below the x-axis. So that means our derivative is below 0. So that means that we have a negative slope. And then on the other side is positive, which means we have a positive slope. And again, negative slope to positive slope, that's the minimum. So that is also true. So that means it's E. Okay, looking at this next one, it's going to be kind of weird. So it says, suppose that f and g are differentiable functions with domains negative infinity to infinity. AKA, we can take a derivative of either of them, and we don't have to like worry about like some like weird exception. Like any value we look at is going to work. Also suppose that f is an increasing function. So I'm going to underline that. Increasing function, that means it's always going up. That also means that f prime is bigger than 0, because that's increasing, and g is decreasing. Well, that means that g prime is less than 0 everywhere, right? If f is always increasing, then the derivative always has to be positive. If g is always decreasing, the derivative has to be negative. And then g is less than 0, aka g is negative for all x. What can we conclude? Well, the first thing they're talking to us about is our derivatives. And it's talking about f of g of x. So let's think about what our derivative of f of g of x is. And this one's saying is bigger than 0, so positive, less than 0. It's always going to be 1. It's always going to be 0, or we don't know. So let's put d dx of f of g of x. Well, we have one function inside another, so this is going to be chain rule. So we do chain rule. We do our derivative of the outside, in this case, f. We're going to keep the inside the same, and then we're going to multiply the whole thing by the derivative of the inside. Okay, yeah, that's the chain rule, but like, how does that help us here? Well, this I always know is negative. Don't know why I put a little dot there. But we're plugging into f prime. And what do we know about f prime? It's increasing. That's always going to be positive. So this whole thing is a positive number. But we're multiplying it by something, by g prime of x. And what is that? That's always a negative number. Well, positive times a negative is also going to be negative. So that means our derivative of f of g of x is always going to be negative. So we're going to say it's going to be less than 0 for all x. Okay, so going on to this next one, we're given it's saying suppose f is a differentiable function such that f of 3 is -2 and f of 7 is 6. Which of the statements below must be true? Well, first I'm going to kind of draw out this picture. So I'm not very good at drawing, so we'll see how this comes out. F of 3 is going to be like -2. 2, this is 3. And f of 7 is going to be +6. So the question is, which of the following must be true? Well, there exists some c between 3 and 7 such that f of c is 0. And we're going to say, because we can take a derivative, that means that it must be continuous. In other words, because this has to go from here to here, there's no way I can draw this where I avoid a y value of 0. If I have to put my pencil down here and draw it to the next dot, no matter what I do, if I go like that, oh, I hit it right there. If I do like that, well, I hit it right there. If I try to do something like weird, and I go like, whoa, like that, well, first off, this is no longer like a function because vertical line test. So that one wouldn't even count. If I did something, if I did something like that, no matter which way I draw it, like I'm going to have to cross over the middle. So we're going to say that is true. Now be careful on this one. A couple of these are actually going to end up being true, like more than one correct answer. So I think it's just going to be a pick all that apply. So don't just stop there. So there exists some c in the interval from 3 to 7 such that the derivative is 0. So this first thing, just to go back a little bit, was from the intermediate value theorem, which is saying that if you have something above and something below, you're going to hit everything in the middle. This would be mean value theorem when you have your derivative. Mean value theorem is saying that if I draw the secant line, aka the line from these 2 points, and I take the slope, somewhere in the middle, there's going to be a spot with the exact same slope. So like if this looks like that, there'll be somewhere in the middle with the exact same slope. So let's figure out what the derivative of our secant line is. So, not derivative of secant line, the slope of the secant line. My bad. So this would be, x1, y1, x2, y2, right? Just basic slope. So 6 minus -2 over 7 minus 3 is going to be 8 over 4, which is 2. So because we got 2, we know that there's definitely be somewhere in the middle where our derivative is going to be 2. But we don't know if there's going to be anywhere where the derivative is 0. Like, it could just be a flat line where everywhere the derivative is 2. So we cannot say anything about that one. It could be true, but we do not know for sure. It has to be 100% certain. So there exists somewhere in the interval that f of c is 2. Well, this one's also going to be the intermediate value theorem. And this one's also going to work. The same way that we have to cross over this middle spot, if I say like this is 2, we also, no matter how we draw our line, eventually I'm going to cross over 2 as well. So that one is going to be true. There exists some c in the interval such that f prime of c is 2. That's going to be our mean value theorem again. And what we got for the slope of our secant line was 2, so that actually is going to be true. And f prime of c is greater than 0 for all c. That's not true. If we think about drawing this line however we want, I could go down and then up, in which case there's a spot where our derivative is negative. So we can't say that. So that's going to be wrong. So it's going to be A, C, and D on this one. Moving on. Given that f prime of -2 is equal to 0, and f double prime, so the second derivative, x times x minus 1 squared, what statement is true? only one of these statements is true. Okay, so let's think about what does it mean that f prime of negative 2 is 0, and then gives us our second derivative. Well, when your derivative is 0, it is a critical point. So that means that we could be a max, we could be a min, we could be neither. But there's a good chance that we're either a max or a min. And one way we can check is we can use our second derivative test because we know what our second derivative is. So what our second derivative test is that you plug your critical point into your second derivative, minus 3 squared, minus 2 times 9, we get negative 18. So that means our second derivative there is negative. Well, second derivative, that tells you your concavity, right? If you're positive, that's concave up, which looks like that. And if you're negative, you're concave down, it looks like that. So in this case, we're negative, so we're concave down. And we know we're a critical point, so we're at this spot here. So the question is, are we a maximum or a minimum? In this case, we are a maximum. We know we're not a minimum. We're not an inflection point because our second derivative isn't 0. And then because we're at a critical point, we're neither increasing or decreasing. So that means B must have been the only correct answer. And that's that.